This conference will now be recorded.
So, very good evening. Today, very good evening. Today, we'll be discussing about nuclear reactor and nuclear fusion. Little bit. Nuclear fission we had already discussed, and fusion also we had discussed little bit. But there are few more important points which we need to learn about nuclear fusion. So first we'll learn little bit of nuclear fusion, and then we'll learn about nuclear reactor. So as we had discussed earlier, also nuclear fusion reaction. What is nuclear fusion? It is the process in which two light nuclei combine or to fuse to form a single heavier nucleus is called nuclear fusion. And see, to fuse two light nuclei to form a single heavier nucleus, you need extremely high temperature. You need to do this reaction at high temperature. Very good evening, Deepa. We'll be today learning about nuclear reactor, and we'll learn few important things about nuclear fusion. So we had already discussed little bit about nuclear fusion. So I'm just discussing the main points here today once again. Basically, proton-proton cycle and carbon-nitrogen cycle I'll be discussing here. So nuclear fusion is actually the process that there are two small or light nuclei. They will combine to fuse or combine together to make a bigger nucleus. Okay, and in this way we see that the binding energy of the single one, if suppose this has mass m and this has mass m1 and m2, we'll see the mass m will be less than the sum of the mass of this, and that the excess mass, so there is mass difference, then defect. So this defect into c square according to Einstein's mass energy equivalence, this equivalent mass energy will get converted into binding energy. Okay, all right. So let us today discuss the fusion process, which is the source of energy in sun and other stars. Okay, so we'll be discussing fusion as a source, or the source of source of energy in sun and stars. Okay, so we have already learned that the sun has been radiating energy at the rate 3.6 8 into 10 to the power 26 joule per second. 26 joule per second. This is a watt also. Okay, so this is the energy, rate of energy radiation from the sun, and the sun is actually radiating energy for several billion years. So what is the origin of such energy, such tremendous amount of energy, and it is how it is keep on radiating energy without being cooling off. Today we'll see that the explanation satisfactory explanation was given by H. Bethe. Explanation was given by H. Bethe. So explanation for what? How sun and all the stars are radiating energy for billion years without being cooling off. So what is the reason behind that? So that is the thing Bethe had explained. What he explained that proton or the hydrogen hydrogen nuclei or proton that means 1H1. Hydrogen nuclei or proton are abundant, okay, are available in sun or stars at very high temperature and pressure. Okay, so there are hydrogen atoms or the protons inside the stars or the sun at very large temperature and pressure. So this extremely high temperature which exists within the like within the sun and stars, here there is a suitable condition for nuclear fission to occur. Suitable environment inside the stars for protons combine combines to make make helium. Okay, helium. So when the hydrogen gets converted into helium or vice versa in the opposite direction, so reactions happens. So when this happens, like hydrogen gets converted into helium nuclei, then it releases a huge amount of energy. It releases a huge amount of energy. Now see, this is actually the fusion reaction. You can see this plus energy. Here two protons are actually getting proton nucleus are combined or fused together to form heavier nucleus. helium, but that is so this is the helium ion, so which are produced from helium ion when fusion reaction happens inside the stars or the sun. Okay, so mainly the fusion reaction of two hydrogen to make helium, or in the opposite direction also helium reproduces the hydrogen. So this mutual conversion, hydrogen to helium, helium to hydrogen, during these processes actually there will be huge amount of energy release, mainly when two hydrogen nuclei are combined to fuse and to make helium ion, helium atom. So that is the forward reaction, and this is the main reason for the energy produced in the sun or the stars. So there are two cycles of taking place of this fusion reaction. Fusion reaction means, see, mainly the reaction, right, proton plus proton fused to helium. Okay, so this is the main fusion reaction which occurs in the stars or sun in two different cycles. So one cycle is called proton-proton cycle. Proton-proton cycle. Okay, and second one is called carbon nitrogen cycle. Carbon nitrogen cycle. Okay, so these are two different cycles of reaction to happen, fusion reaction to happen. So first we will discuss what are the possible reactions, thermonuclear reactions in the proton-proton cycle. So let us erase this carbon nitrogen cycle. Okay, so in the proton neutron, sorry, proton, I'm sorry, this will be proton cycle. Proton will be twice. Proton cycle. During this cycle, what happens? There are equations which occurs here. First, two protons, they will combine or fuse to produce a deuterium 1H2 plus positron plus neutrino plus 0.42 MeV. So first reaction is proton combined to make deuterium, and then here, since you have positron, there will be electrons also. This gets converted into gamma. That means there will be release of energy. So how much energy? Okay, so they will produce 2 gamma. This much of energy. I'm sorry. This is 1.02 MeV. Okay, and then see, we have got deuterium. Now two deuterium combines. Two deuterium will combine. Two deuterium will combine to make light nucleus of helium. He2, this is 3. This is light nucleus of helium along with gamma plus 5.49 MeV energy. Okay. So first proton combine to get deuterium. Along with that, energy release will be there. And then two deuterium combine to get this light helium atom. Okay, helium nucleus. Now these such two helium, two light helium nuclei, they will be actually after fusion reaction, sorry, this is 3 alone, 3. These two combines to get one helium, then two protons will be regenerated, two protons, and there will be release of energy 12.86 MeV energy. Okay, so these are the sequence of the reactions in the proton-proton cycle which occurs in the stars or inside the sun. So two proton combine to give you deuterium, two deuterium combine to give you light helium nucleus, and then two light helium nucleus. After fusing, they will produce a real or the desired helium nucleus 2He4, which is called alpha particle also, and then the rest will see 1H1. These are also produced in this reaction as part of the product. So two proton will be produced, and along with that there will be 12.86 MeV energy released in this reaction. Now look, you are needed two helium, light helium, two. So if you undergo only one cycle or once the reaction, then you may not get two. So it is said that all three processes has to repeat. This all three processes like processes or sequence of the reaction has to repeat for twice to get two helium light nuclei, and they then combine to give you the proper helium nucleus, and along with that there will be proton generated, and also 12.86 MeV energy is generated. This is actually proton-proton cycle. So mainly if I write the proton-proton cycle, reaction of the proton-proton cycle in one line, reactions PP cycle, proton-proton cycle, in one line the equation will be 4H1 plus 2 electron, then helium nucleus will be formed, along with that 2 a neutrino, 6 gamma, and this is 12.6, sorry, 27.6 MeV. এই হচ্ছে, so this is the reaction, like all the reactions in combination. If we write this is a single reaction, sorry, single line, in single line I have written the whole equation. So there will be 4 protons required and 2 electrons as reagent, and then there will be helium nucleus produced. Along with that, some 8 gamma, sorry, this is 2, this is, these are actually neutrino, and this is gamma, 6 gamma, 2 neutrinos, these are neutrinos, these are not gamma, these are neutrinos, like this. Okay, then 26.7, sorry, 26.7 MeV energy will be released. Okay, so this is the proton reaction. This is in brief. Now we'll go to the carbon and nitrogen cycle. So in carbon nitrogen cycle, okay, let me clean this portion. So we'll see carbon nitrogen cycle now. Carbon nitrogen cycle. So in the carbon nitrogen cycle, what happens? The necessary thing is that there should be a carbon nuclei which successively absorbs protons in the series of steps. Okay, so in this case, carbon is the main reagent. You should have carbon 612, and along with that, suppose a proton is getting fused, then it actually gets converted into nitrogen, nitrogen 13.7, that is the light nitrogen. .93 MeV energy will be energy generation will be there, and there will be gamma emission. Okay, now this is again radio. See this one, if you combine with again, this combine to actually this will actually break. This is radioactive nucleus, so this breaks into two. One is carbon C13, which is again carbon C13 is also radioactive, and carbon C13 will give rise to, sorry, nitrogen 713 give rise to carbon 613. These are not B. You should not consider this as B. Okay, so it will actually give rise to protein, sorry, positron, then there will be gamma emission, mainly gamma emission plus the energy. Okay, so okay, let me just repeat this thing again. See, the carbon, upon taking or after fusing with the proton, it gets converted into this nitrogen nucleus. This is actually a radioactive one, so it will spontaneously decay into carbon C13, which is again a radioactive element. So C13 plus positron and also neutrino will be generated. Along with that, there will be 1.20 MeV energy released. Now see, since this is carbon C6, this is unstable or radioactive, so this also will actually disintegrate. Okay, so or if here see, when there are protons, it will actually combine with the proton and regenerate this nitrogen 7 and 14. So this is actually the end product of the reaction. So carbon nitrogen cycle, see, carbon gets converted to nitrogen, nitrogen gets converted to carbon 13 C13, and that carbon C13, upon absorbing a proton, it will actually be converted into nitrogen 14 and nitrogen 714, which is actually stable 1. Now what it will do upon absorbing another proton, see, nitrogen 713 14, this will absorb another proton. Now see, you will get oxygen 15, light oxygen nuclei. Along with that, there will be gamma and energy released 7.39 MeV. And finally, what it will do, finally, this oxygen 15 8, that is unstable. Since it is unstable, so it will actually gets converted into nitrogen 15 again, plus positron, then neutrino, plus 1.71 MeV energy. Okay, so this is for, because this is actually unstable, it undergoes this. And then finally, this nitrogen 15, nitrogen 15 and 7, nitrogen 715, what it does, it actually, upon absorbing one proton, will give you C612, this is natural one, then 2He4. See, at this stage the helium is produced, plus 4.99 or 5 MeV energy will be released. Okay, so this is the final step of the reaction. See, if we write in terms of single line of this equation, sorry, this reaction, then in single line, what we have to write? We have to write proton combines with carbon C12, it gets converted into helium, but in between there are few reactions we had written already, so those things we are not writing, so it will gets converted to C12, C612, then 2 proton, 2 neutrino, plus 3 gamma, and along with that this enormous amount of energy, 24 MeV. Okay, so this is actually the nitrogen cycle. So in the nitrogen cycle, what happens? Carbon nitrogen cycle. Carbon, upon absorbing a proton, gets converted into nitrogen 13 and then releases energy. That nitrogen 13 is actually unstable. That will break into different nucleus. So here in this case, carbon 13. Now this carbon 13, upon absorbing proton, it will produce nitrogen 14. This is the natural nitrogen. And now this nitrogen, upon absorbing proton, will get converted into light nucleus of oxygen isotope, and then that isotope will break, because this is unstable, break into nitrogen 15. This is again a radioactive material. So in that case, see this, upon absorbing this proton, it gets converted into 612 and 2He4. This is actually the helium or the alpha particle, helium nucleus or the alpha particle, and along with that 4.99 MeV energy is getting released. So the whole reaction in one line, if we want to write, then 1H1 plus C612. So this is the proton plus carbon, and that will give rise to helium. Along with that, carbon regenerated, and these are the byproducts, along with 24.8 MeV of energy. So this is how carbon-carbon cycle and proton-proton cycle, they are responsible for the sun to have this much energy, or the stars to have this much energy, and they are continuously radiating for several billions of years. So we have learnt about fusion reactions in sun and stars. Now today we'll learn about nuclear reactor also. So you can see this is the simplified figure of nuclear power plant. So in the nuclear power plant, what you have something called reactor pressure vessel, where these nuclear thermonuclear reactions are happening. Then during thermonuclear reactions, basically here thermonuclear reaction, fission reaction happens inside the reactor, fission reaction. So during fission reaction, we see there will be fast neutron produced. Fast, that means high energy neutrons also will be produced. But those neutrons will generally have a tendency to escape rather than igniting another reaction to make the reaction into chain reaction. So for that reason, those thermal, like fast neutrons, are actually slowed down by moderator. So what we'll do, we'll just in brief we'll discuss that when a reaction happens, fast neutrons will release the energy to the water. That water actually gets converted into steam. Actually that steam, now there are two chambers, like water high pressure chamber, and this is actually, sorry, water, yes, this is water high pressure. Here actually steam high pressure, it will go to turbine. Steams will go to turbine. Turbine will actually be rotated by high pressure steam, and that high pressure steam will rotate the turbine, and along with the turbine there will be generator connected, and that generator will actually create electric power. So this is the brief idea about nuclear reactor. Now we'll see inside this vessel itself or nuclear reactor itself, what are the things there, will learn great detail about this particular box, that is the nuclear reactor core. So look, in the nuclear reactor there are few important parts of the nuclear reactors. So there are fuel. First of all, let us, okay, so this is actually a typical nuclear reactor, figure of nuclear reactor. Nuclear reactor, you can say reactor core also. So this nuclear reactor has different parts. One is the fuel, nuclear fuel. Nuclear fuel. So what are the nuclear fuel? So you know you need to have a nuclear fissionable nucleus to produce nuclear energy or the fission reaction to happen. So you need fissile or fissionable nucleus as fuel, like see fissionable nucleus like uranium 35, then you have plutonium Pu. Okay, so plutonium, or I'll write in terms of, so this is uranium 230, then Pu, Pu 239, and etc. So like these are the nuclear fuel, and see in the nuclear reactor, see fuels are actually made in the form of rod, in the form of rods. See, this is the rod, this is one rod, this is another rod, these are another rod. So fuel elements are these. Okay, so these are the rods, fuel rods. These are made of maybe either uranium or some other fissionable material. So these are the rods. Now, and these are also fuels of nuclear reactor. Now you go to the, so nuclear fuel, then we need to have moderator in it. So first one was nuclear fuel, then second thing is moderator. We have seen that during the fission reactions, there will be fast neutron produced, fast neutrons, and should be what is the desired role of the fast neutrons? They will ignite another uranium or another fissionable materials. Okay, so here uranium, after see, I had actually last day I had told you, suppose you have something, so suppose this is actually high, this is energetic neutron comes over here, so this will actually uh, produce two daughter, because it is splitting, and there will be three neutron, first neutron, these are neutron. So these fast neutrons are having a tendency to escape the nuclear reactor itself. So to keep them, we have to slow them down. So that's why moderator is used to slow down the the fast neutron, so that those fast neutron becomes thermal neutron, and thermal neutron actually takes place in fission reaction. Okay, and these thermal neutrons, when they are actually stopped by moderator. Moderator means moderator actually uh, moderators, beryllium oxide, graphite, heavy water. So these are the moderators. So heavy water, graphite, beryllium. These are beryllium. These are the materials used as moderator in the nuclear reactor. Now there will be control rods. Control rods here I'll show you. So third is control rod. This is used, as the name indicates, control rod. These are the rods which are used to control the reaction. How? See, these control rods actually can control the ratio of the neutron, number of neutrons, or the, yeah. So this control rods, what they do, if you have excess amount of neutron, so those excess neutrons will be absorbed by this control rod. So here you see control rod generally made of cadmium. Cadmium rods are called control rods. This cadmium are used to control the reaction in the reactor. Okay. Now there will be coolant. Coolant means, see, in this case, very high energetic electrons are actually stopped by heavy water. And how this motor, so see, the energy released by a neutron to the moderator will be getting converted to huge amount of heat. Okay, so the temperature will be very large. So that heat energy will be actually heating up the whole system or the core. That's why there should be coolant. Generally, liquid sodium or heavy water can be used as coolant. The role of the coolant is to make the reactor cool. So coolant, and then shielding. Shielding effect, because during this reaction, nuclear thermonuclear reaction, there will be various energetic particles like alpha, beta, or gamma radiation will happen, and that's why the core of that is all protected by shielding, such that the radiations produced in nuclear reactor will not penetrate through the body of the workers. That's why there is a concrete wall made in the made outside, just outside the reactor. So this is the brief idea about. So this is the wall, concrete wall. Concrete wall actually gives not only thermal insulation is there already. This radiation shield, it acts as a radiation shield, so that the workers does not get exposed to the radiation. So these are the few parts we have learned. Like important part is actually fuel, then you have moderator, fuel, moderator, then controller. So see control rod, and then coolant and wall shielding wall. So these are the few important points: fuel, moderator, control rod, coolant, shielding. You need to actually remember examples of each of them. Then you will be able to answer the questions. There will be some questions, some places there will be question that coolant, what is used as coolant? Generally beryllium, sorry, this is sodium, liquid sodium or heavy water. So this is about nuclear reactor. So we'll actually stop it here for today, and this is how we complete the chapter nuclei. Next day we'll take up various problems, numerical problems, depending on this fusion, alpha decay, beta decay, gamma decay, etc. So therefore we'll stop it here today. Deepa, if you have any question or doubt, you can ask me now.